VLSos here. This is a video lesson on complex numbers. Let's take a look at an equation that we weren't able to solve before we were introduced to imaginary numbers and included the imaginary unit in our mathematics. The imaginary unit, we gave the symbol I, and it's equal to the square root of -1. This is the imaginary unit to use this value in our mathematics, and it's all that we need to include in order to handle all situations that have a negative under the radical. Let's see how it's going to come up in this problem. I have a quadratic equation set equal to 0. We can think of this as a polynomial of degree 2, so I expect there to be 2 solutions. If I graphed this, I would see that this parabola would not intersect the x-axis. So in finding the solutions, or the roots to this equation, I'm not going to find x-intercepts, because as we'll see, they're going to become imaginary solutions. They're going to include the imaginary unit. I'm going to use the quadratic formula, where a is equal to 1, b is equal to -6, and c is equal to 34. In this case, the quadratic formula is x is equal to -b, or 6, plus and minus the square root of b squared, or in this case 36, minus 4 times a times c, all over 2a, in this case 2. Taking another step, I'm going to divide the 6 by 2 to get 3, plus and minus, and under the radical I have 36 minus 4 times 1 times 34. 4 times 1 times 34 is 136. So 36 minus 136 is -100. I will have a -100 under the radical, still divided by 2. Next step, 3 plus and minus. We can now deal with the square root of a negative number. The square root of the negative factor of this number is going to become our imaginary unit I, and the square root of the remaining 100 is simply 10. So the square root of -100 is 10i, still divided by 2. And I can list these factors now in simplest terms by reducing this fraction 10i over 2 to 5i. 10 divided by 2 is 5. So my 2 solutions is 3 plus that 5i and 3 minus the 5i. These are the solutions to this quadratic. There are 2 of them, as we should expect of a degree 2 polynomial. They have I in them, so they are imaginary numbers. But more than that, we're going to call them complex numbers. A complex number is one of the form a plus bi. A complex number is a single value, but it must be expressed as the sum of 2 components, because we are distinguishing between a, the real component, and the part that includes the imaginary unit we call b, the imaginary component. And I is grouped with the imaginary component. It's the imaginary unit. These solutions are 2 values, and each of these values contains 2 components to express this complex solution. Both of these solutions have a real component of 3. one solution has an imaginary component of positive 5 and the other a negative 5. And of course, they're complex numbers because they have two components each to express them precisely, and one of them includes the imaginary unit. We call these complex roots. Roots is another name for solution, and complex because those roots are complex numbers. When we get complex roots as the result of a solution process, they're always going to come in pairs, where the pair of complex roots will share the fact that their real components are the same, and their imaginary components are equal in magnitude but opposite in sign. Equal in magnitude of 5, but opposite in sign because we're adding one and we're subtracting the other. We call complex roots that are together like this complex conjugates. And complex conjugates have a couple of properties. Complex conjugates come in pairs as complex roots to some equations. And it will always be true that when you multiply complex conjugates, in this case, in general form, we have two complex conjugates. They have the same real component A. They have their imaginary component B is equal in magnitude but opposite in sign. We can see that we're adding here and subtracting there. Let's see what happens when we multiply these two complex conjugates. I'll get, by distributing, A squared plus A, or A times negative BI is minus BI. BI times A is plus BI. And positive BI times negative BI is negative B squared I squared. If we simplify this, we can see that this term drops out. They cancel each other out. From the previous lesson, we know that if we square I, it becomes negative 1. I is the square root of negative 1, so if you square it, it undoes the radical and leaves negative 1. So if we multiply the b squared, or the minus b squared, by negative 1, then this gets simplified to a squared plus b squared. It is always the case that when you multiply complex conjugates, it will simplify to this form. And there is no imaginary unit in this form. These a's and b's are real. What happens when we add complex conjugates? Here we have a pair of complex conjugates that we are adding. In general, if we drop the parentheses, we'll get A plus A, and this, well, if these are complex conjugates, we have to subtract. The plus BI, the positive BI plus the negative BI will cancel out, leaving 2A. When we add complex conjugates, what's left is just double the real component, and the imaginary component is eliminated. So adding complex conjugates becomes a real number.